perfect fluid, meaning a fluid where there's no friction, no dissipation, no viscosity, then such a configuration of fluid flow, like this vortex, would be stable for all time. It would last forever. Now that got Kelvin to thinking, well, where can I find such a perfect dissipationless fluid? These kind of fluids do exist. Superfluid helium is an example of this. But back in the 1800s, they didn't know about superfluid helium. It wasn't discovered until the 1900s. So where could he find one of these? Well, fortunately or unfortunately, in the scientific literature at the time, there was a well-known mistake. Well, back then they thought it was gospel. They thought it was for real, but now we know it's a mistake. And the mistake is known as ether. What is ether? Well, ether is supposed to be just such a perfect dissipationless fluid that fills the entire universe. Why did they think such a thing exists? Well, they knew a lot about waves. They knew about water waves. They would see a wave in the water and they would say, well, it's really the water shaking around. And they knew about sound waves and they would realize that that's really just the air shaking around. And they knew light had wave-like properties, but they didn't see anything shaking around. So they sort of invented this thing and they called it ether, and they said that's what's carrying the light wave. And they could see light from stars very, very far away. So they knew it had to be dissipationless. There could be no light in order for no loss such that the light made it to us from the stars. So Kelvin thought that this ether was this perfect dissipationless fluid. So he immediately concluded that a fluid flow configuration like this in the ether would be stable for all time since there's no loss. So what are these sort of complicated fluid flow arrangements in the ether? What do they correspond to? Well, he came up with another important idea. He said, well, maybe this is an atom. Maybe this thing is actually a hydrogen atom. So a particular configuration of fluid flow like this would correspond to hydrogen, and you can imagine more complicated arrangements of fluid flow, maybe one like this. And in this picture, I mean, the fluid is flowing around this imaginary loop, and the fluid is flowing also around this imaginary loop, and the two loops are linked. And this might be a hydrogen molecule. And maybe you could have even a more complicated arrangement. Let's see if I can draw this appropriately. I'm not going to be able to do this. Like this. And maybe, okay, now I've gotten myself in trouble. Well, okay. All right. I'm not even sure I can close this up, but I don't know. Anyway, so maybe this is something like lithium, some more complicated knot of. So what I mean by this is that the fluid is flowing around this line wherever the line goes. Actually, that looks like it can be unentangled. Yeah, let me just change across in there. Okay, that looks like it's a non-trivial knot. Like this. All right. Anyway, you know what I mean. Sorry about that. This is how you can tell I'm not a topologist. Topologists can draw knots on the first try without getting messed up. Okay. Anyway, this idea of fluid flow configurations in the ether associated with knots or links being the physical reason for atoms, which is known as Kelvin's vortex theory of the atom, was actually extremely popular for some number of years in the 1800s. Why was it popular? Because it gave some idea of why it is that atoms are discrete and immutable. They're immutable, they last for all time, because these fluid flow configurations, this is Kelvin's theorem, the fluid flow configuration in a perfectly dissipationless fluid is stable for all time. And they're discrete because the people even back in the 1800s, they realized there was hydrogen, there was helium, there was lithium, but there was nothing in between them. And similarly, you have this knot configuration, you have this knot configuration, you have this knot configuration. They're discrete again. So people were very fond of this idea. But after about 10 years or so of studying this, they gave up on it. And the reason they gave up on it was because it actually didn't seem to predict anything about atoms. It didn't predict their masses, it didn't predict their spectra, it didn't predict their chemistry. It just seemed to be unrelated. Nonetheless, there were some people in the world who were very fond of this theory and refused to give it up, even in the face of all physical evidence. And one of the most, the strongest proponents of this theory was Peter Tate, which is rather surprising because initially Peter Tate had said that this theory couldn't be right because of all the reasons that everyone else later gave him, which is that it didn't predict anything about the atoms. But somehow or other, he changed his mind about it during those 10 years, and then he became a strong proponent of the theory. Anyway, we now know that this has nothing to do with why atoms exist. But Peter Tate, at the time, was very fond of it, and he really spent much of the remainder of his life well, actually, he spent a lot of the remainder of his life golfing. He was this huge golf fanatic, and he taught his son to golf, and his son was a golf champion and played in the British Open and so forth. And actually Peter Tate wrote some very important papers about fluid flow over golf balls. But besides that, he spent much of the remainder of his life, besides thinking about golf, he spent it thinking about knots. And while the application that he was thinking about, this vortex theory of the atom, turns out to be nonsense, his work on the theory of knots, the mathematical theory of knots, actually turned out to be extremely groundbreaking. So what Peter Tate was trying to do is he was trying to compile a list of all possible knots that you can draw on a blackboard. Like here's the first one, here's the second one. This one might be the third one or whatever. And then just keep compiling this list, and somehow or other, from that list, he wanted to conclude something about the periodic table of the elements. Well, the mathematical theory of knots became a very rich field of mathematics, which people have studied for the last 150 years, since Peter Tate's time. And Peter Tate is, I think, rightly viewed as the real father of this field. And during his exploration of knots, he actually hit on what is still considered one of the most fundamental questions in knot theory. And that's, how do you know, incidentally, I'm now taking a detour from physics into mathematics and knot theory, but I'll come back to physics shortly. So Peter Tate's fundamental question is, how do you know if you draw two knots on a blackboard, like here's my first simplest knot, and then maybe I'll draw another sort of not quite as simple knot, like this. How do I know if this knot and this knot are really the same? In other words, can this thing be unentangled without cutting any of the strands and turned into this thing? So how do you know if they're the same? Well, in this particular case, it's pretty clear that they are the same. You could just unfold this and it's an open loop, and you say they're the same. But for very complicated knots, it turns out it's not so easy to see. And it's very hard to tell if these things are the same or if they're different. Anyway, mathematicians have studied this problem of trying to distinguish knots from each other for a long time. And one of the tools they've come up with is the idea of a knot invariant. Knot invariant. And a knot invariant is really just a mapping of a knot, or a picture of a knot that you have drawn on a blackboard, via some set of rules or an algorithm to an output. And the output could be a number, or it could be a polynomial, or something like that. And the rules are constructed such that topologically equivalent inputs have to give the same output. So in other words, if the two inputs into the set of rules can be deformed into each other without cutting any of the strands, then the output has to come out the same. So this can tell you immediately if two knots are different. If you put the two knots into the same set of rules, you get two different outputs. You know immediately the way you put it had to be not deformable into each other by, without cutting the strands. So just to put some meat on this story, I'm going to give you an example of a knot invariant, which is extremely useful for us, known as the Kaufman invariant. Kaufman, after Lewis Kaufman. And it's very closely related to the famous Jones polynomial. And maybe if we have time, I'll explain the difference. And there's really only two rules of how you calculate the Jones polynomial. The first thing you do is you choose a number and call it A. A stands for a number. Maybe complex. A equals number. Okay. The second rule is that if you ever see an open loop, you replace it by the quantity minus a squared minus a to the minus 2, and that combination is usually called D. And the next rule, the last rule, is, so let's call this rule 1, this is rule 2, is if you say two strings crossing over each other, you can replace them by A times two strings that don't cross over each other this way, plus A inverse times two strings that don't cross over each other this way. And I'm going to draw it, so let's call this 2A. And I'll make 2B, which is exactly the same rule, except all the diagrams are going to be rotated by 90 degrees. So that's just a convenient thing to do, so that later on in the talk, you don't have to rotate your head by 90 degrees. Okay? And those are the only rules of the calculating the Kaufman invariant. So to show you how this works, we're going to evaluate the Kaufman invariant for this funny looking knot here. Okay? Everyone still with me? Okay. All right. is this something everyone knows and has seen many times? Have some people seen this? Okay, some people have seen this. 50%? More
Maybe
than 50%.
less, maybe less.
Maybe yes, maybe not. I'll keep going, okay. It looked like it was sort of 50%. So I'll keep going, and we'll I'll hopefully return to things that other people aren't aware of shortly. Anyway, so how do we how do we apply these rules to say this knot? So first thing we're going to do is we're going to focus in on this upper crossing here, and this knot. Draw a little loop, dotted line around it, so we're focused on it. And then we're going to apply rule 2a because it's a crossing that looks like this. And so we replace that by, let's see. So we replace it by a times something that looks like this, plus a inverse times something that looks like this. And then we complete the knot exactly as it looks here. So complete the knot like it looks here, complete the knot like it looks here, and complete the knot. Okay, is everyone with me? See how that works? Okay. And then we have to do the same thing for the lower crossing. In both cases, the lower crossing looks like this. So I'll just do that really quickly. So then we get a times something like this. So I'm now going to be replacing this guy. That coefficient there is here. So like this, plus a inverse times something that looks like this, plus a inverse times, now here would be a times this, plus a inverse times something that looks like this. Okay. All right, now we apply the first rule that every time I see an open loop, I replace it by this quantity d. So then I get a squared times d squared, plus this cancels this, I get plus a, no, those cancel, plus d, plus these two cancel, plus d cubed, plus a minus 2 times d squared. Okay, and then we're going to notice that a squared plus a minus 2 is exactly minus d. So this term and this term end up giving me a minus d cubed, which cancels this term, and I get d in the end. That's supposed to denote excitement. So the reason that I'm excited about this is that this has done exactly what we wanted it to do. We know that secretly this knot we have up here is an open loop. Okay? And an open loop, the Kaufman invariant is supposed to give it a value d. And even though I folded this up and made it look more complicated, when I put it into the Kaufman invariant is smart enough to realize that this is just the open loop. So it gives me the same value d. Okay? It's clear how that works? All right. So now one thing, being that I'm in a computer science building, I should point out that this is obviously a recursive algorithm. And so if I had a knot with 100 different crossings on it, it would take me 2 to the 100th different steps. Because each time I resolved this, I generated two diagrams, and then I had to resolve those. And so this one gave, this had 2 crossings, so there were 4 diagrams. So it gets complicated very quickly. But at least in principle, you see how it can be done.
So all the knots reduce to loops at the end?
All the knots, well, I can successively remove crossings, and each time I remove a crossing, every diagram that's remaining has one last crossing, so I have to be able to reduce everything down to something with no crossings. So everything has to reduce down to loops. You may get loops inside loops. That can come out. But that also gives you a value of d. That will give you a value of d for each loop, independent of whether they're inside or outside each other.
Is it known? Are there 2 known knots which are not isotopic, which give the same Kaufman invariant?
Yes. Yes, there
What's
are.
the simplest example?
I think the simplest example has quite a few crossings, actually. I think something like 12 or 16 crossings. I don't remember offhand. It's an open question as to whether there is any non-trivial knot which gives you the same Kaufman invariant as the open knot, as the unknot, if you like. That's, I believe, an unknown question. But it is known that there's more than one knot with the same Kaufman invariant. So the Kaufman invariant doesn't distinguish all knots from each other. All right. So should I do a little bit of honesty and advertising? I was going to skip this, but it seems like a sophisticated audience, so more than I had expected. So maybe I'll do a little bit of honesty and advertising to be honest about things. Okay. And this has to do with the difference between the Jones polynomial and the Kaufman invariant. So to understand the difference, this here, what I'm going to do is I'm going to just consider for a second a little piece of a knot that looks like this. Okay, but what I mean by this is that the rest of this is connected up somewhere. I'm just not concerned with what's out there. I'm going to evaluate the Kaufman invariant of this little twist. Well, using this rule, 2a, I can replace that by a times this plus a inverse times this. Okay, and then this thing is replaced by a d. This thing can be straightened out, and then I get a d plus a inverse times a straight line. And then AD times A inverse, actually, with a little bit of algebra, that's minus A cubed times a straight line. Okay? So now you should be throwing tomatoes at me. Because I promised you that the Kaufman invariant was supposed to give you the same result as long as two things could be deformed into each other without cutting any of the strands. And it's pretty clear that this can be deformed into this without cutting any of the strands, and yet their Kaufman invariants differ by a factor of minus A cubed. So why am I lying to you like this? Well, what I claim is actually this and this are not the same picture. They can't be deformed into each other without cutting any strands. And the reason is this: you really should think of these things as having a little bit of width, being a ribbon rather than a string. So if you sort of draw this as a ribbon like this, and you tried to pull it straight, you would get something that looked like this. Okay? Rather than something that looks like this. All right? So that's a little bit of truth in advertising. We'll see later, a little bit later, that this is actually has to do with spin statistics theorem. Okay? And let me come back to that.
But instead of doing this, you can turn this like this.
No, you're gonna, if you do that, you're gonna mess up the rest of the knot. You have to leave the endpoints the same. So you're gonna get this twist somehow. You can't, I mean, if you imagine connecting up the top and the bottom, you'll discover that this thing is actually fundamentally different. So, okay. All right. Having given that introduction to knots, let me turn and relate this now to physics. So, do I need this? No. Get rid of this. So I want to introduce the idea of a topological quantum field theory. Topological. This is the one that doesn't work. Quantum field theory. Or TQFT. So a topological quantum field theory is a quantum system where amplitudes depend only on topology and not on the detailed geometry. Now, this is a little, if you're not from a physics background, this is a little hard to explain, but let me try to explain it based on a couple principles about quantum mechanics. So, people who didn't come from a physics background, how do you feel about quantum mechanics? Are you good with it? You're not good with it? You're happy with it? Okay. All right. So let me actually introduce quantum mechanics in the method that Feynman used to think about quantum mechanics. So Feynman's way of understanding quantum mechanics is to say if you want to calculate some amplitude of getting from some initial configuration to some final configuration, what you need to do is you need to sum over everything that can happen in between. So you calculate some propagator or partition function of your system, and what that is a sum over all paths from the beginning to the end of e to the I action of that path. My h bar. Is this something that's at least conceptually familiar to most people? Okay. Good? Happy? Okay, good. In a topological quantum field theory, so here I'm going to draw, here's a two-dimensional system here. And for the remainder of the day, I'm going to be talking about two-dimensional plus time. And I'm usually going to draw time in the vertical direction. Time goes upwards. So here's a two-dimensional system I've drawn, a two-dimensional disk plus time going upwards. And here's a particular process that can occur. So I have a two-dimensional system as a ground state. There's some particle hole creation event, if you like, kind of like this. So you can go particles appearing from the vacuum in particle-antiparticle pairs. Maybe at some, these propagate along, at some later time, maybe another particle hole creation event coming out of the vacuum. Maybe these particles wrap around each other and they come back and they annihilate at some later time. Like this. And this is some process that can occur, and so it has to be added to the path integral. It's an allowed process, therefore it's in this sum. It's in this sum. Okay. Now, in a topological quantum field theory, I'm going to draw another picture here. It's the same two-dimensional disk. And then draw a picture that looks kind of like this. And then it goes under like this, like this. Okay. So in a topological quantum field theory, the amplitude for this process and the amplitude for this process have to be the same, because they can be topologically deformed into each other without cutting any of the strands. So in topological quantum field theory, the amplitudes depend only on the topology of the process and not on the detailed geometry. Okay? So what we should immediately be thinking is that that tells us that this factor here, e to the I action, must be a not invariant, because it's a mapping that goes from the not to the output, which depends only on the topology of the not that I put in. Okay? Now this connection between topological quantum field theories and not invariance was something that was very famously made by Ed Witten, a string theorist and mathematician who won a Fields Medal for this along with Jones. Oh, I forgot to tell you, I gave you this whole thing about this undoing this twist, and I neglected, oh, this is bad of me, I neglected to mention that the difference between the Kaufman invariant and the Jones polynomial is that the Jones polynomial correctly is the Kaufman invariant modified such that this and this are equal. So you've just added a term such that these two things end up having the same value instead of having a different value. Anyway, so Jones and Witten won the Fields Medal, the highest award in mathematics, for their work connecting topological quantum field theories to knot theory. So rather remarkably, one of the things that Witten did was he actually made the explicit mapping between topological quantum field theories that were known and somewhat understood at the time and the particular non-invariant that you get out of them by evaluating e to the I action. And if there's space here, let me put it here. The particular mapping is if you know this mapping SU2 level K, that's the name of a particular topological quantum field theory that was known. This thing maps directly to the Kaufman invariant parameter A given by the number I e to the I pi over 2k plus 2, and or little ad is 2 cosine pi plus 2. So it was a direct mapping between topological quantum field theories and this thing, the Kaufman invariant.
Sorry.
Yeah.
What distinguishes between TQFTs? Is it the action that they're assigned to different?
Yes, the actions will be different. So there's a whole bunch of different TQFTs, which each of them will have a different action going into this path integral. Yeah. So actually, I should also. So I can back up at this point to just a comment. When we did this calculation, which I just erased, so usually I have more space on my board, so I'm erasing things that I need. But what we calculated was this thing equals minus a cubed times the straight line for the Kaufman invariant. So you'll notice that minus a cubed is just a phase. This thing is actually just a complex phase at magnitude 1. And this, we have this picture where we tried to pull this straight. It came out looking like this. So what this tells us is that a particle that twists around itself once picks up a complex phase. And this is something that we know from quantum mechanics. When a particle is rotated around, it picks up a complex phase. A particle with spin. All right? Okay, so now I can come to the definition of this word here, topological phases of matter. A topological phase of matter is a physical system whose low energy, long wavelength physics is a topological quantum field theory of this type. And rather remarkably, these things are not just a figment of my imagination, they actually exist. So I can sort of make a semi-complete list of where these things are believed to exist, and they come in various different types. So the one that's most known to exist are topological quantum field theories of type SU2 level 2, and if you like, that means you're just supposed to use the value of A given by k equals 2 in the Kaufman invariant in order to calculate its action of a given path. So these things, there's a fractional quantum Hall effect state called the nu equals 5/2 state. For those of you who don't know about, I'll say more about fractional quantum Hall effect in a little bit, for those of you who don't know about it, but it's something that occurs in two-dimensional semiconductors at very low temperature and high magnetic field. There's strontium ruthenate superconductor films, superfilms. There's helium 3A superfluid films. And there's a couple of others that are proposed, including topological insulator supersurfaces. Insulator supersurfaces. And then there's SU2 level 3 type, of which there's only one known, that's fractional quantum Hall effect for the fraction of fifths. Now I should say, to be completely, and then there are others that have been proposed. There's lots of Hamiltonians that you can write down, toy models, where you can convince yourself the low energy theory, or the low energy description of that Hamiltonian is a topological phase of matter. But the ones that are actually being observed in the lab, sort of, this is more or less a complete list. And of this complete list, the evidence is reasonably strong for this one, and somewhat weak for the remaining ones at this point. The experiments are actually quite difficult to do, but and so I wouldn't say that any of this evidence is ironclad as of yet.
What about the 12/5 phase?
This one? The evidence is marginal on this, but I'd say one should be optimistic about it, because what the numerics tell us about this system is that there's a phase transition, so that there's a phase transition very close to the value of the experimental parameters. And it goes from sort of a trivial fractional quantum Hall state, which is uninteresting, to this non-trivial fractional quantum Hall state, which is interesting, very close to the experimental value of the parameters. And so what is known is there is a fractional quantum Hall state. It's not known which type it is. But the reason it's optimistic is because if it turns out to be the wrong type, one could tweak the experimental parameters probably enough to push it over the phase transition to the other one, at least in principle. What's not optimistic about this is this one is only seen at much lower temperatures than this one. So this one you can see up to a fraction of a Kelvin. This one you really need to be below 100 millikelvin to see it at all. So it's much harder experiments from just a technical standpoint. Now maybe poll the audience here. So should I say a little bit more about fractional quantum Hall effect, or talk about general properties of TQFTs and why we're going to be able to do things like compute with them? Want to hear about quantum Hall effect? Okay. A couple comments on quantum Hall effect. Yeah. So fractional quantum Hall effect is, so here's a theorist picture of fractional quantum Hall effect. what you do is you start with two-dimensional electrons. And you might ask, well, how do you get your electrons to be two-dimensional? What you can do is you build a semiconductor heterostructure. In other words, two different semiconductors stacked on top of each other, such that there's a nice interface which trap the electrons at this interface. So the electrons are confined to live strictly in two dimensions. Then you add a magnetic field, a huge magnetic field to these things, and you cool it down to low temperature. So basically going to low energy. And what you get out is quantum Hall effect. That's a rather grossly simplified view of the story, but there are many of these quantum Hall states which are parameterized by a number which we call nu, which is basically the dimensionless ratio of the number of electrons divided by the magnetic field, and you make it dimensionless by multiplying by a factor which has Planck's constant, speed of light, charge of the electron on it. So there's, each time you come to the right value of this fraction, or near the right value, every time you get to the right value of this, well, you can change magnetic field in the experiment continuously, and when you get to certain values of this ratio nu, what you see is a dissipationless state of matter occurring, like a superfluid. So you'll see fractions like 1, 1/3, 2/5, 7/15. I mean, you see a whole bunch of these, of which, and each one of these is a separate phase of matter with its own properties. Of this list of fractional quantum Hall states which are seen, very few of them have these interesting topological properties. And it's only these guys, well actually 7/2 also lives in this category, sort of a mirror of 5/2. Pretty much those are the only ones which have these properties. Now you might ask, being a physicist, physicists like to have, they have this concept of when you have a high energy theory and you go down to a low energy theory, what you want to do is you want to eliminate the high energy degrees of freedom in some systematic way, sort of integrate out the high energy fluctuation modes, and you're left with a low energy theory. So what you get is you want to get down to some topological quantum field theory as a low energy theory by integrating out high energy modes. No one really knows how to do that in most cases in any controlled way. So the arguments that get you from the high energy theory of just two-dimensional electrons in a magnetic field to the low energy topological quantum field theory is actually a very roundabout argument. The evidence is very strong by this point, but it's not a very direct argument, unfortunately. Or maybe fortunately, because that makes it interesting enough to work on. But experimentally, there is one big hint that, that these quantum Hall effects really are topological quantum field theories. And the hint comes from the only experiment that experimentalists find easy to do in these systems. So the only experiment you do, so here's your two-dimensional sample that has some shape. And the only experiment that's easy to do is you attach electrical contacts to it. And you run current in one contact, out another contact, and you measure the voltage between the two other contacts. That's the only experiment that's easy to do. Any other experiment is really hard. But these experiments are really nice. So if you do the experiment in this geometry that I've drawn here, you always get the same answer. Voltage equals 0. That's a rather boring answer. You would get the same answer for any superconductor or superfluid. No voltage is supported between these, independent of the current that you flow. But you can change the geometry by switching the current and voltage. So now the current and voltage leads across. So measure current comes out here, voltage comes out here. And what you get is voltage is 1 over nu h over e squared times current, where nu is a quantized fraction like 5/2, for example. And you get this voltage out independent of the shape of the sample, independent of where you attach the contacts. Okay? All that matters is that you've topologically crossed the current and voltage leads. So what you have here is something that depends only on the topology of the sample and not on the detailed geometry. So that's a hint that you're going to have something come out that's topological. There's one more comment about fractional quantum Hall effect that I should say, which is, if you come from a high energy theory background, there's this sort of general paradigm of having a high energy theory and like the grand unified theory of the universe, and you come down to low energy, and there's some symmetry breaking. So there's like the electroweak symmetry breaking that occurs at the electroweak scale, and the low energy theory is less symmetric than the high energy theory. But in fact, what we have here is exactly the opposite. We have symmetry emergence. The low energy theory has the very high symmetry of a topological quantum field theory, whereas the high energy theory had no particular symmetry at all. So the symmetry comes out at low energy.
Can I ask a question? Yes. Suppose you took the upper connector for your voltage, the connector, the equivalent, and you allow that to walk down on the surface of your... So you
Down here.
move that sort of gradually down towards the lower one, over the surface rather than the boundary. How would you see the voltage?
Yeah, so this is a complicated story that actually ends up depending on details. You have to ask how much current goes around it this way and how much current goes around it that way. So it's not obvious what happens next.
It's perfectly continuous. There's no...
Yeah, there's nothing sudden happens there. I think. So I mean, there are experiments like this, and they have complications associated with it. I mean, if you do, you can ask the same question about moving the current contact, and you discover that you can't actually inject current into the center of a fractional quantum Hall sample at all. So if I tried to put my current contact in the middle here and push it in, push current in like this, in fact, current doesn't flow out from a point, because, I mean, you can think of this way, this thing is a perfect Hall conductor. So you try to push current in one direction, and in fact, it only goes in the opposite direction. So you end up with current flowing around in circles instead of going out towards the edges. So it becomes dissipative. So it's sort of it gets to be a complicated experiment. So let me turn a little bit to some interesting properties of these systems. So general properties of TQFTs. General property of a TQFT is that if I have, here's my two-dimensional system, and suppose I have a system with two particles and two antiparticles in it, like this, my claim is, even given that I've told you where the particles and the antiparticles are, there's in fact two degenerate states that describe this, exactly the same energy, but orthogonal or linearly independent states. So let's call the first one 1, and we'll call the second one 2. And these are, I'm going to draw the same picture. Okay, that was not very good. They're supposed to look the same, so I apologize for that. Why is it that it can be more than one of these? So typically, if you take like a metal or an insulator and you tell me where all the electrons in the system are, you've told me the state of the system. You tell me where all the electrons are, where their spins are, and so forth, what their states are. In this case, you haven't told me the state of the system. Why not? Well, because if you think in terms of their space-time history, time going up like this, you can imagine that these two were pulled out of the vacuum this way, or these guys were pulled out of the vacuum this way. Okay? And these two are topologically different ways of creating that configuration. And the system remembers what its space-time history was. Now, to show you that these two things are topologically distinct, I have to show you that they're inner product. You know, that they have the inner products of two things that are linearly independent. So to do that, so I've given you the kets. Let me take the corresponding bras. I need more room. So corresponding bras look like exactly the same, except they're turned upside down. So this is the corresponding bra. This, and the corresponding bra over here. So this one is one bra. That, two bra, looks like this. And to take an inner product between 1 and 1, all I do is I squeeze these together. And if I squeeze these together, I end up getting two loops like this. And then I evaluate the Kaufman invariant of this. And this is where the d squared. Okay? If I do the same thing over here, it's pretty easy. You bring those two together, and you discover that 2 and 2 gives you two loops, and that's also d squared. But if I take 1 on 2, like this, 1 on 2, I have 1 that looks like this, and 2 that looks like this, and that gives me only one loop, and that's where the d. Okay? Yes.
I don't understand why, in what sense is that the bra, in what sense is this taking the inner product?
Right. So you might say that I'm defining it that way, but in fact, this is true from a quantum mechanical perspective in a topological quantum field theory. That the states of the system are characterized by the topology of their space-time history. So in order to, this is the same statement as saying that the action, the amplitude of getting from initial vacuum to the final vacuum is given by the Kaufman invariant, which is this thing that I wrote, in this Feynman formalism. E to the I action is the e to the I action is given by the Kaufman invariant. So that's the same statement as saying, if I cut a system in the middle and I call that a state of the system, I should be able to get amplitudes by looking at the Kaufman invariant and taking two of them
So this
together.
is like a nice pictorial way of showing what the theory actually says.
Yes, exactly. It's an equivalent way. This is the content of the statement I made before. That e to the I action gives you the Kaufman invariant.
So the edge on is computed to be actually like time reversal. That's what you do.
Yes. Yeah. Yeah. More or less. Yes. So at any rate, just with these equations, that 1 on 1 is d squared, 1 on 2 is d, 2 on 2 is d squared. It's clear that 1 and 2 are linearly independent objects. The only exception to that rule is if d happens to be 1. You come over here and you realize that for k equals 1, you get d equals 1. So SU2 level 1 is special. That one has no interesting degeneracy in the sense that these two states will be the same for SU2 level 1. And unfortunately, in this whole list of fractional quantum Hall states, which I wrote down, there's 1/3, 2/5, 7/11, or whatever they are. Almost all of them are related to SU2 level 1. And these guys are the only exceptions. They're still topological, but they're topological in a rather trivial way. So one can add one more thing to the story, that if I wanted to take, that I can insert between the bra and a ket, I can insert some complicated knot, like this, some braid. This guy goes over here, maybe this guy goes like this, over, under, this, and this guy maybe this. I can insert some complicated braid, and then I can just evaluate 2 braid 2 by evaluating the Kaufman invariant of this knot. Okay? Now, why is it that people, you'll know this better than I do, why is it that people are excited about this? Well, had I, instead of calling these things 1 and 2, I called them 0 and 1, you would have immediately thought of a qubit. So the power of suggestion there. Someone once said that any idiot with a two-state system thinks they have a qubit. The history of the field may tell us that. But in fact, there's a really good reason to try to use this thing as a qubit for quantum computation. So the general scheme, topological quantum computation, is really cooked up by a couple people, Mike Friedman, another Fields medalist, Alexei Kitaev, probably the people most credited for thinking this up, and for realizing why it might be a very useful thing to do. But the general way in which we imagine computing with this is you start with your system at some time here, you initialize your system by pulling particles from the vacuum like this, then you do some computation. So this starts this initializes the Hilbert space, the state in the Hilbert space if you like. Then you do some operation on the Hilbert space. This is some unitary operation on the Hilbert space by braiding the particles around each other in some complicated way. And then at the end of the day, you can try to measure them by trying to return them to the vacuum. And some of them will return to the vacuum. Others of them will not return to the vacuum, and that's the readout. Okay? Now, why is it that this is considered a good thing to do? Well, in order to understand why this is considered a good thing, a good way to do quantum computation, one has to understand why it is that quantum computation is hard in the first place. The reason quantum computation is hard in the first place is because it's really hard to keep quantum systems isolated from their environment. If noise comes into, if you think of this sort of conventional pictures of having lots of two-state systems, which you call qubits, like spins, for example, that can be spin up or spin down. If a photon comes into your system and flips over one of your qubits, you've made an error, and you have to go through great lengths to protect your system from these kind of errors. So let's imagine what happens if some noise comes into this system. So here's some noise, say a photon or a phonon or something, and it hits this particle here. This is a particle moving along. So what's going to happen? What's going to happen is instead of moving in a nice smooth line, it's going to wiggle around. But the knot that you formed is still the same knot, independent of whether it wiggled or not. So you end up doing the same computation so long as you end up with the same topology. So that's considered to be the great advantage of building a quantum computer this way. All right. So in the last few minutes, I can actually tell you a little bit about the actual experiment that some people are trying to do to demonstrate to themselves that these fractional quantum Hall states really do have this type of non-abelian, I use the word non-abelian, this braiding statistic. I haven't used the word non-abelian statistic yet, so I'm not going to use it now. Does that sound like a good use of time? Okay. All right. So the particular system in question that people are doing the experiment on is this one, the fractional quantum Hall effect at nu equals 5/2. And one needs to know a couple of facts about quantum Hall effect. One important fact, so that here's a quantum Hall sample. It's a two-dimensional sample. So you have electrons in here. It's in a large magnetic field, so there's a magnetic field B through the plane of the board. Their electrons are being held into the sample from the side, so there's some sort of electric potential holding them in here. So what you have is you have crossed electric and magnetic fields, so there's charge running along the edges this way. This is sort of always happens in quantum Hall experiments. You get these nice edge states. And I drew them backwards here. Let me draw them the other way. This way. Okay. So the experiment that people are going to do is going to take advantage of the fact that these currents of particles run along the edges. So what one can do is one can squeeze the edges together like this. So now your edge states kind of run like this. But if you get the edges close enough together, occasionally a particle can jump from one edge and backscatter. Then what one does is you make a sample that looks like this. So now the particle can backscatter here, or it can go over and it can backscatter here. And what you look for is interference between particles taking the short route and particles taking the long route. Okay? So let's call, let's see how we're going to do this. Well, okay, so let's call this route here short, and this longer route we'll call long. So this thing is basically like a Fabry-Perot interferometer. Incidentally, in the experiment, you can actually vary the length of a longer route, and what you're supposed to see is interference fringes, the same way as if you have an interferometer and you change its length. You get interference fringes. So what you actually get out, the output here, out, is then, like you say, there's some tunneling amplitude we'll call T1 at this point contact, tunneling amplitude T2 at this point contact. So what you get out, the outket, is T1 times the short distance plus some phase associated with the length of the longer path times T2 times the long path. Is that something that people are relatively happy with? Good. So what you actually measure is the probability of being backscattered, so it's going to be T1 squared plus T2 squared plus 2 times the real part, e to the I, phi, T1 star T2 times short on long. Okay? And since the length, this e to the I phi, this length term, this additional phase, this interference phase, can be varied in the experiment, you can vary this term and then measure, basically measure how big this short on long overlap is. Okay? So let's see if we can calculate that short on long using the calculated variant. So draw this picture again. All right, so here's the picture. It's like this. And, okay, we have to be a little careful here. So I'm going to draw time up this way. So first, before I send a particle through the short path like this, I have to ask, where did this particle come from? And the place it's going to come from is, I'm going to pair create it with a partner at this early time here. So in the space-time diagram, I'm going to create two particles, two particle-hole pairs, a particle and an antiparticle pair, and send one of them through this short path and then bring them back to here. Is that clear what I just did? Okay. Now, correspondingly, I could, so this one's short, I could have taken him through the long route. That, in which case the space-time diagram would have looked more like this. Okay? So this is short, this is long. All right. So short on long here, in order to calculate short on long, I just turn this guy upside down and put him on top of this guy, so I get something that looks kind of like this, short, and then long. And that's one loop, and so that has value d. Okay? All right. Now I'm going to change the experiment a little bit. What I'm going to do now is, before doing this experiment, I'm going to add a single particle to the center of this loop. Okay? Just one particle there. So what happens now? Well, I have to ask, where did this guy come from? So the way I'm going to get him in there is I'm going to pair create someone over here and move him in there before the experiment. So I'm going to do the same thing over here. Create, pair, move him in there before the experiment. So let me keep track of so now I'm going to keep track of this particle as well. So in this picture over here, at some time long ago, I'm going to pair create, move this guy in before I do the experiment. It comes out like this. Whereas over here, I pair create some time long ago, move him inside, and then importantly, this long route goes around where the particle is. So now it looks like this. Okay? Is everyone happy with that? Clear what I'm doing? Happy? Happy? Yell, scream, this is the stunning conclusion. Okay, so now when I take short and turn it upside down and long, what I end up getting, okay, so short kind of looks like this. No, I want to turn, long is on the bottom, so I want to make short on long. Short on long. So long is on the bottom, so it looks kind of like this. That, and then it kind of looks like this. This guy goes inside, goes back like this. Then short, looks like this. This guy looks like this. Okay. So that's short on top of long. Is that clear what I did? Just turn short upside down, dropped it on top of long. This thing is two linked loops. And so in order to find out what the amplitude of short on long is, I have to evaluate the Kaufman invariant of two linked loops. So let's do that. I have 4 minutes left before the hour, so let me now do this experiment. Okay, I'll do this quickly because we already figured out explained what the rules were of the Kaufman invariant. Oh, here are the rules sitting over here. So, so two linked loops looks like this. Okay, so first I'm going to apply the first rule to, so I'm going to use 2b first on the upper crossing. That thing now is A times something that looks like this, and then under this, plus A inverse times something that looks like this. Okay, and then we have one more crossing here. So that becomes A squared times two loops that look like this, plus another something that looks like this, plus something that kind of looks like this, plus A minus 2 times 2 looks like that. And that is then A squared times D squared, plus 2 times D, plus A to the minus 2 times D squared. A squared and A to the minus 2 gives me another factor of minus D, so it's minus D cubed plus 2D. Okay? Now, Oh gosh, I erased it. Oh, I'm sorry. So, I erased the important thing. So I apologize. The important thing here is that for SU2 level 2, D is actually square root of 2. I had the formula up for what A was supposed to be, and D ends up being square root of 2 in this case. And so if you just plug that in here, you discover square root of D cubed with a minus sign, 2 square root of 2, ends up giving you 0. So this is the crucial result. The point is, when there is a quasi-particle or particle in the center of that loop, this term in the interference actually vanishes, and you don't see any interference fringes at all. And it turns out, if you do it more carefully, it's an even-odd effect. When there's an even number of particles inside that loop, you see the full interference term. The amplitude is 1, D. Whereas when there's an odd number of particles inside the loop, the interference vanishes altogether. And that's the signal that people are trying to see experimentally. And the status of the experiment is very complicated. Some people are very optimistic that that's what it's seeing. There's some amount of dissent as to whether it's actually been seen or not, because there's a lot of experimental complications which make it a much less ideal system than you would like. But if it's true that this thing is, this effect is observed, that I think will be the first convincing observation of a non-trivial topological phase of matter, or a TQFT in nature, that we've been able to construct. And in principle, that opens the door to doing topological quantum computation, at least in principle. So I'll stop there and take any questions, and thank you for your attention. Questions, comments?
So the Kaufman characterization is a mathematical thing. So why does it map perfectly on the expectation values in physics?
Yeah, no, that's a good question. So you might ask, why isn't this something more complicated?
Yeah.
Well, SU2 level 2 is it's a very simple topological quantum field theory. It's one of the simplest ones. If you're going to find a non-trivial topological quantum field theory, it's maybe not surprising this one is it. There is, so why is it that this one should be so prevalent? I had this list of topological quantum field theories, and many of them came out to be SU2 level 2. It turns out that there's a mapping between types of superconductors and superfluids directly to SU2 level 2. That's sort of, it's not a great explanation. It just happens that SU2 level 2 is one that occurs frequently.
It's sort of a lucky thing that Kaufman came up with this one.
It's yeah. Actually, and the truth of the matter is that some of the abelian phases that you don't care about are not quite SU2 level 2. The Kaufman-Jones category actually isn't unitary. You need SU2 level 2 is very closely related to it, but is the unitary case, so it's a little tricky, but it's pretty much this. Yeah.
In this experiment you just described, presumably you have an independent way of measuring the number of particles in these cells.
You kind of don't.
But then all you could say is that you're measuring them.
Yes, but you know.
But you're not really testing the theory.
So you don't know. What you do know is you have a way of knowing pretty closely how much you've changed the number of particles in the inside. So now you can ask, how well are you calibrated in the experiment? There's a lot of experimental issues associated with that, which people can argue about. But at least, the way the experiment is actually done is there's several things you can vary in the experiment. You can move the edge in and out to change the length and the phase. You can actually, there's a top gate that you can charge up